Hi everyone. So this video is basically about choosing the learning rate for stochastic gradient descent. So in the last video when we introduced SGD, we discussed the concept of convergence of SGD, or theoretical guarantees for convergence, and we will elaborate on that concept in the next video. But basically what's important to note is that in practice we don't really see convergence of SGD. It just provides a guideline for us, right? So because we don't typically run until SGD converges into an optimal solution, but we use early stopping or some mechanism to stop the training after a certain number of training iterations, right? So the lesson learned from the basic convergence results that we discussed last time is basically that the learning rate should decay with time. So I should start with larger steps and then I have smaller and smaller steps, but it shouldn't decay arbitrarily quickly, right? So I should control how the learning rate should decay, right? So because if it decays too fast, then that could be problematic, right? And the intuition is very simple, other than the formal intuition that we provided last time through a second order Taylor series approximation of the coast. Other than that, the intuition is that basically with a large learning rate, you are exploring the parameter space. With small learning rate, you are fine-tuning and finding the optimal, to find the optimal solution within the current neighborhood, right? So you can think of it this way. If I have a parameter space that looks like this, then I want at the start, right? I want at the start to explore as much as possible from that parameter space. And then, so let's say it looks like this, right? So I want at the start to explore as much as possible from that parameter space and then get into a neighborhood of the optimal coast. And within that neighborhood, you use a small learning rate, right? So that's basically the intuition, is that at first you start with a large learning rate to explore as much as possible in the parameter space. And then you have a small learning rate because you are within a neighborhood. And remember all the approximations that we had for regularization schemes like early stopping and L2 regularization, they were assuming that we are within a neighborhood, a local neighborhood of the optimal solution, right? So you reach that neighborhood by having a large learning rate at the start. Now, a common strategy is to start with an initial learning rate. Let's call it epsilon 0. And then you have a terminal learning rate. Let's call it epsilon tau. So you decide on the value of epsilon tau and the value of tau. So tau is a number of iteration, right? Is an iteration index, right? So typically you choose tau as the number of iterations required to make a few hundred passes, and this is just empirical wisdom through the training set. So after a few hundred epochs, right? An epoch is a complete pass through the training set. And epsilon tau is typically on the order of 1/100 epsilon 0. And then you have a linear interpolation between epsilon 0 and epsilon tau in the first tau iterations. And then you fix to epsilon tau. And basically the intuition behind this strategy is that you start with a large learning rate, epsilon 0, and then you minimize it, you shrink it by a multiplicative factor, and then you reach this epsilon tau, which is much smaller than epsilon 0, and then epsilon tau is very small already, so you don't get smaller than this, right? And then you fix the epsilon tau, right? You don't get smaller than this because from the theoretical result, we know that we don't want the learning rate to decay, to vanish too quickly, right? So you don't want it to be very small, so that, because if it's very small, then basically the parameter updates have a negligible effect on the cost function, right? So that's a common wisdom or a common strategy. Start with a initial learning rate. That's for the basic SGD without any of the extensions that we'll discuss later in that section. Start with an initial learning rate and then linearly decaying until you reach a terminal learning rate after tau iterations, and then you fix at epsilon tau. And you could combine that with early stopping or any other way that decides at which training iteration you should stop training. Now, how to choose epsilon zeros, right? So if we choose that common strategy, then the choice of the learning rate boils down to a choice of the initial learning rate. Now, this is a non-trivial thing to do, and it requires typically a lot of trial and error, right? And typically, it would require that you try out several learning rates for a small number of iterations, and then pick the one that leads to the fastest decay in the training error, basically. And that means that this learning rate results in the best exploration at the start. So remember, the initial learning rate role is to explore the parameter space and reach a neighborhood around the optimal quickly, right? So that's the intuition behind that wisdom of trying a small number of iterations, maybe 100 epochs, and see if you got in the neighborhood of a good solution, right? And then if you do that, then you can, through the decay in the learning rate, you can fine-tune the solution, right? And in general, the factors to take into consideration is that if epsilon zero is very small, then this will result in slow training, which can get stuck early. If epsilon zero is very large, that could result in unstable training that oscillate between regions that are far apart in the parameter space, right? And one thing to keep in mind while designing SGD or any optimization algorithm that's based on gradient descent for deep learning in general is that the computation time should not be too sensitive to the number of training examples. So in particular, it should not scale with the scale of the training examples. And the reason behind this requirement is that typically you want to handle situations with very large data sets, right? So you want your algorithm to be robust such that it can handle a very large data set. It could scale with very large data set. Thank you.